Nebraska Sandhills, 1896, no trees, stone, or lumber within 100 miles. The federal government named this the Great American Desert, 19,000 square miles of grass-covered dunes. In the 1870s, the horse-powered baling press arrived, turning loose straw into dense, stackable rectangular blocks. They were meant for animal feed and winter bedding. They were not meant for building. But in 1896, the first documented straw bale schoolhouse rose from those plains. Compressed grass, 4 feet thick. Plastered with locally dug clay mud when lime couldn't be sourced, the schoolhouse stood. In 1902, it was reported damaged. Not from structural failure, someone left it unfenced, and cows ate the exposed straw. What those builders didn't fully understand was the thermal magic. A Nebraska winter drops to -20, a summer crosses 100. Yet inside walls 4 feet thick, the temperature held. Organic mass at that density refuses to transmit heat quickly. The wall absorbs exterior heat, delays it by 8 to 12 hours, and delivers it when the outside is already cooling. No compressor, no refrigerant, no electricity. Agricultural waste was outperforming modern insulation. The global insulation market is now valued at over $29 billion annually. Industry standards arrived by 1945. Straw bale had none of those standards. It barely has one today. By the end of this video, you'll discover why and how to build one. Welcome back. Subscribe so you never miss what the insulation industry hopes stays forgotten. Every ancient civilization facing extreme temperatures independently arrived at the same conclusion: mass is the system. The ancestral Puebloans began constructing Pueblo Bonito at Chaco Canyon around 850 AD, 650 rooms across 5 stories. Its sandstone and adobe walls ranged from 1 to 3 feet thick. This was a thermal battery. Archaeological surveys show interior temperatures 15 to 20 degrees below summer highs without any cooling. They built in a high desert where summer temperatures regularly crossed 100 degrees and winter nights dropped to single digits. The mass of those walls absorbed the day's heat and delayed its transfer past the point where the exterior had already cooled. The D shape wasn't just aesthetic, it was passive solar. The north wall blocked cold winds while the plaza welcomed the sun. These people proved that the most efficient thermal system we have isn't a machine, it's the very matter we choose to build with. The history of building isn't just about shelter, it's about thermodynamics. Next, we look at how to apply this today. The wall kept the desert out, not by blocking it, by outlasting it. 300 miles south, Taos Pueblo was under construction by 1325 AD. Its adobe walls range from 70 centimeters thick at the base to 35 centimeters at the top. UNESCO designated Taos Pueblo a World Heritage Site in 1992. Its residents still refinish those walls annually with fresh adobe plaster. A maintenance ceremony performed continuously for 700 uninterrupted years. The building code that governs most of North America has no prescriptive pathway for the material that built the oldest continuously occupied structure in the Western Hemisphere. On the other side of the world, the Hakka people of Fujian province in southern China arrived at the same solution. Beginning around the 10th century, they constructed their Tulu, circular or rectangular earthen fortresses, from rammed earth walls measuring up to 180 centimeters thick at the base and rising 5 stories. 46 Fujian Tulu received UNESCO World Heritage designation in 2008, with documentation confirming that some have stood for more than 700 years without structural failure. Interior temperature surveys of occupied Tulu show year-round stability within a 5 degrees Celsius range, despite exterior swings exceeding 30 degrees. More than 23,000 people still live in the Yongding district Tulu today. Their thermal stability comes entirely from wall mass. No insulation manufacturer's product appears anywhere in their construction. In Iceland, Norse settlers arriving from Norway beginning in 870 AD faced a subarctic climate. With no accessible timber, they built the Torfbear, turf farmhouses with walls of compressed peat, soil, and layered grass reaching 2 meters thick at the base. Interior temperatures inside these structures held between 10 and 15 degrees Celsius during winters, when exterior temperatures dropped below -20. The Arber Open Air Museum in Reykjavik preserves surviving examples. This tradition ran continuously from 870 AD until the last Icelandic turf farm was abandoned in 1966. Over 1,000 years of documented thermal performance from compressed organic material. Different continents, different materials, different extremes, identical physics. Modern building science calls this phenomenon thermal mass insulation, the capacity of a dense, non-conductive material to absorb, store, and slowly release thermal energy. Unlike conventional insulation, which resists heat transfer by trapping air in fiber matrices, mass insulation slows the rate of transfer through sheer density. The heat gets in. It just takes so long to complete the journey that exterior conditions have already reversed, before the interior feels the effect. Straw compressed into a 3-string bale at a density of 7 to 8 pounds per cubic foot has a measured R value of 2.0 to 2.9 per inch of thickness. A standard 3-string bale is 23 inches wide. That produces a wall with an R value between 46 and 66 before any plaster is applied. Oak Ridge National Laboratory, one of the primary thermal testing facilities in the United States, conducted guarded hotbox tests on plastered straw bale wall assemblies and documented R30 as a conservative baseline for standard 18-inch bales. 3-string assemblies at 23 inches measured R-48. For comparison, a standard 2A6 wood frame wall insulated with fiberglass batt, the construction method used in the majority of American homes, achieves R19. The straw wall more than doubles that performance using agricultural waste. The fire performance numbers are equally clear. ASTM E119 fire resistance tests conducted in 2006 on straw bale wall assemblies found that walls plastered with clay achieved a 1-hour fire resistance rating. Walls plastered with cement lime achieved 2 hours. ASTM E84 surface burning tests conducted in 2000 recorded a flame spread index of 10 and a smoke developed index of 350, both below the International Building Code maximums of 25 and 450 for concealed insulation. The wall that burns more slowly than the insulation inside most American homes has no mandatory code pathway in most American states. At the University of Nevada, shake table structural tests conducted in 2009 subjected plastered straw bale wall assemblies to simulated seismic events the plastered assemblies held. Researchers confirmed that straw bale walls behave as structural diaphragms under lateral loading, demonstrating resistance that met or exceeded conventional stud frame construction under equivalent conditions. The science isn't uncertain, the performance isn't disputed, so why is there not a straw bale wall in every new American home? The answer has nothing to do with physics. It has everything to do with what the physics threatens. The global building insulation market was valued at $29.3 billion in 2023. Owens Corning, the largest fiberglass insulation manufacturer in the world, reported revenues of $9.7 billion that same year. Johns Manville, CertainTeed, Rockwool each generates billions annually from a product category that American building codes legally require every residential builder to purchase. The business model depends on one thing: replacement. Fiberglass batts compress and lose R value over time. Spray foam develops voids. Rigid foam boards crack at seams and settle. The average American home requires insulation remediation or replacement within 15 to 25 years. That cycle keeps the market growing. A straw bale wall, properly constructed and plastered, carries a documented service life well beyond a century. The Haslow House in the Nebraska Sandhills, built in 1913 from baled straw, was still wearing its original stucco coat 100 years later with no insulation intervention of any kind. One construction event, no replacement cycle, zero recurring revenue for any manufacturer. The North American Insulation Manufacturers Association, NIMA, represents fiberglass and mineral wool producers in Washington. Its member companies authored ASTM C665, the standard specification for mineral fiber blanket and batt insulation. Those ASTM standards became the basis on which the International Energy Conservation Code evaluates all residential insulation. A product without an ASTM designation has no number that an energy code can reference. No number means no compliance pathway. No compliance pathway means a building inspector who encounters straw bale walls has one default response: denial. Not because the wall is dangerous, because no one in the code cycle had any financial reason to write the table that says it's allowed. Straw bale received no ASTM designation until 2016. The International Residential Code added Appendix S in 2015. That is 119 years after the first straw bale schoolhouse stood in Arthur County, Nebraska. France approved professional construction rules for straw bale in 2012, formally designating it as common technology. The UK has built straw bale schools, community centers, and residential developments since the early 2000s. Germany, Austria, New Zealand. Each country encountered the same material and chose to write a standard. America chose to leave building inspectors with no table to reference for 119 years. But you do not need anyone's permission to understand the physics. Here is exactly how to build one yourself. Before you source a single bale, 3 pieces of information determine everything. First, your jurisdiction's current position on straw bale construction. Check the most recent edition of your local residential building code and search for Appendix S. If your state has not adopted the 2015 IRC Appendix S or passed independent straw bale legislation, you'll apply under the Alternative Materials and Methods Clause, which means engaging a licensed structural engineer before permitting begins. Second, your climate zone. Straw bale works across all climate zones but demands moisture management that changes significantly by region. High humidity environments, the Gulf Coast, coastal Pacific Northwest, and the American Southeast require vapor-open plaster systems and aggressive roof overhangs. The bale isn't the weak point, moisture management is. Third, your structural system. Load-bearing straw bale, the original Nebraska method, where the bales carry the roof load directly, is appropriate for single-story buildings in low seismic zones. Post and beam framing with straw bale infill is the correct choice for two-story structures, moderate seismic zones, and most permitted projects. If you're navigating your first permit, post and beam infill reduces engineering complexity substantially. Source 3-string bales with a moisture content below 20% at the time of installation. Use a probe-type moisture meter to verify. Do not estimate. Bales above 20% moisture will begin decomposing inside the wall before the plaster cures, and no amount of exterior coating will stop that process once it starts. Standard 3-string bales measure approximately 16 by 23 by 46 inches and weigh between 75 and 100 pounds. Use wheat straw, rice straw, or rye straw. Avoid hay. Hay retains seed heads and organic nutrients that attract rodents and accelerate biological breakdown inside the wall cavity. Raise every bale course on a foundation that holds them a minimum of 6 inches above exterior grade. This is non-negotiable. Straw in contact with persistent ground moisture will fail, regardless of how well the wall above it is built. Install a capillary break between the concrete stem wall and the first bale course. A layer of bituminous waterproofing membrane or closed-cell foam board that prevents moisture from wicking upward through the foundation. Skip this step, and the base of every wall in the building will draw groundwater for its entire service life. Stack bales in running bond, staggering vertical joints by half a bale length on alternating courses. Drive bamboo or rebar stakes vertically through each new course to pin bales to the course below and prevent lateral movement during plastering. The wall requires a minimum 24-inch roof overhang on all 4 sides. This single detail keeps the majority of wind-driven rain off the plaster surface and extends wall life by decades. Don't frame a straw bale structure with standard eave dimensions. The wall won't survive it. Apply plaster immediately once the bale stack is complete. Do not leave unplastered bales exposed through a rain event. Apply a minimum of 1.5 inches of lime or clay plaster on both interior and exterior surfaces in at least 2 coats, 3 coats on the weather-exposed exterior. Lime plaster is vapor-open and self-healing. Hairline cracks reseal as the lime carbonates over time. It's the correct choice for most climates. Clay plaster on the interior provides hygroscopic regulation that passively buffers interior humidity. For builders in high-moisture climates who can't reliably manage bale moisture during construction, the alternative is prefabricated structural straw panels, compressed straw faced on both sides with oriented strand board. Available with full ASTM E119 fire certification and permittable under standard residential codes in all 50 states. They deliver 85 to 90% of the thermal performance of a site-built straw bale wall with no on-site moisture management required. They cost more per square foot. They eliminate the compliance conversation entirely. Build it correctly and your wall will outlast the insulation in every house on your street by a century. When supply chains break and manufactured insulation becomes scarce, as construction materials did during the shortages of 2020 and 2021, when material costs surged across the board within months, a straw bale wall is already built. It doesn't need a delivery truck. It doesn't need a factory to be operational. It doesn't degrade on a 15-year replacement cycle. The field that grew the material is still producing every harvest. Conventional insulation depends on petrochemical supply chains, industrial manufacturing, and a code cycle that someone is paid to maintain. A straw bale wall depends on a baling machine and a plaster mixer. The ancestral Puebloans solved this at Chaco Canyon around 850 AD. They packed organic and earthen mass into walls and let physics do the rest. Norse settlers in Iceland solved it in 870 AD with grass and peat that lasted 1,000 years. Nebraska settlers solved it again in 1896 with harvest waste that cost nothing. The R value of compressed straw is the same today as it was when those settlers stacked their first bale on the sandhills. The physics still work. The bales are waiting. Now you know not just why this was hidden from you, but exactly how to build it yourself. Subscribe if you love this guide and watch this next video.